Well, we are back again with section 8.2, which picks up right where we left off. This is now, we're still taking samples. All this chapter is about taking samples. But sometimes we don't want to know the average of something. Maybe we want to know the proportion of something. Maybe we want to think through how a population thinks or believes or acts in a certain way. And for that, we're still going to use some of the same ideas. We still are going to do a normal analysis, which means we need to know the mean and standard deviation. But what does the mean have to do with a proportion? Well, we'll see. Point estimates is what we're going to start with. Suppose a random sample of size n is obtained from a population in which each individual either does or does not fill in the blank. Either does or does not believe a certain way, act a certain way, think a certain way. The sample proportion that we denote as p hat, yeah, pretty original, right? Denote as p hat is given by the number of individuals that think that way out of the number of individuals that were asked. Kind of a basic idea of that's what proportion is, right? And this sample proportion, p hat, is a statistic that estimates the population proportion. We do this with polling, right? In a recent poll, 1,745 registered voters nationwide were asked whether they approved of the way the current president is handling the economy. 749 responded, yes, we approve of how or of how the president is handling the economy. So we obtain a point estimate, right? And to obtain the point estimate, we simply divide 749 divided by 1745, and we get 43%. So 43% of the people in that particular poll approve of the way the current president is handling the economy. Well, each time you take a poll, I mean, is it true that 0.4292% of the United States believes that way? No, it's an estimate, point estimate, right? The next time you take that poll, you might get 4.1, you might get 4.3, you might get 4.4, you're probably not going to get 0.64, right? They're all going to be tight right in around what the actual is. And many times we can't know what the actual is, but we take point estimates so we can figure out approximately what it is. And guess what the shape of all those is going to be? Sure, it's going to be normal. Let's get this out of politics and move it into Star Trek versus Star Wars, right? Let's say a poll discovered that 42% of people prefer Star Trek over Star Wars. I personally think that's a crazy idea that less people would prefer Star Trek over Star Wars. I think Star Trek is a much better universe, but that's okay. Imagine obtaining 300 samples of size n equals 10. In other words, we're going to find 300 random groups of 10 people and find the point estimate of those 10 people. How many out of 10? There's one. Another group out of 10. There's a second one. We do that 300 times. What do you think those point estimates would look like? What do you think the distribution would? What if we did size n equals 50? We grab 300 groups of 50 each. What if we grab 300 groups of 100 each? And if we plot all 300 of the 10, all 300 of the 50, all 300 of the 100. Guess what these just might look like? Well, as you can imagine, most of them are going to center right around that value of 0.42. In fact, you might not be able to read this, but with the size n equals 10, the mean of these 300 groups is 0.426. Is that kind of close to 0.42? The standard deviation of this one is 0.160. N equals 50. Does it look even more normal? The mean, interestingly, is still right around 0.426, but the standard deviation has dropped now to 0.072. And with our group of 100, now the mean is actually that 0.42 with a standard deviation of 0.047. It's dropped even lower. So what we're going to discover here is that even though we're not measuring the middle, the average height of toddlers, the average weight of a penny, we're actually measuring how a population thinks. And maybe only 10% of the population thinks this way. Maybe 80% thinks this way. Maybe 72% thinks this way. But no matter where that population moves to, when we take samples, we're going to have a normal shaped curve around that. And if you think back to chapter 6, and in fact you could go back and look at that PowerPoint if you wanted, we had to make sure that our sample size was large enough so that we have room. If we move this normal curve all the way up, it might run out of room because we've only got from 0 to 1. If we have a 0.8, we might run out of room for that tail to develop. So that's why we have to have a large enough sample so that we can squeeze that standard deviation down low enough to be able to get that full tail in on both sides. So that's a pretty important thing, which means that n size, again, matters greatly. A couple things to notice. As the sample size n increases, yes, it becomes more approximately normal. The mean of those groups we're sampling, right? Even though what we're sampling is proportions, all those proportions can be added together and divided by the number of samples to give you a mean. So the mean is going to equal the proportion. And that spread is going to decrease as the sample size n increases. And more specifically, the shape is going to be normal. Remember how I said that we have to make sure we have room for the tails. And as if the population proportion is stated as a very high number, we have to make sure that n is large enough. And I'm not going to bother going through the math of this, though it's a pretty straightforward thing here to go through. As your p-value, the proportion value, as stated, the way a population thinks, the 0.42 Star Trek, as this thing becomes closer to 1, this becomes closer to 0. And if this value gets too low, because either p is very large, close to 1, or close to 0, either way these are balanced, you'll get a value closer to 0. And that means this n value has to be large enough as this gets smaller. And that ratio, here I just said I wasn't going to go through the math, and here I am. If this amount gets too low, the n has to be high enough so that there is this balance to give you room for both tails. And what those people in the big gray building decided to do is say, well, this n sample size, when multiplied by the proportion times the complement of that proportion, has to be greater than or equal to 10. And if it's greater than or equal to 10, we've got room for both tails. Then we can do a good solid normal assessment. Remember, to do a normal analysis, what do you need? The mean and standard deviation. The mean of the p-hat is the stated population proportion. Whatever the population says it is, that's what you're going to use as the mean. And the standard deviation of the p-hat, this is pretty complex looking right there, right? Okay, so, and I don't know if there's a nice, easy way for StatCrunch to go through this. I've not explored that. I'm sure you will, but it's not very difficult to plug this into a Desmo screen or a calculator to figure out what this value is going to be. So I talked about the n has to be large enough, right? You need to have a large enough n so that you can squeeze that standard deviation down enough to make sure there's room for the tails. But you can't make n too big. You can't let it be too big. And that's when you sample people, usually you don't put them back in the mix to potentially sample them again. Think about those pennies. I grabbed 10 pennies out find the average weight, and then I probably set those aside, right? I'm not going to put them back in the pile of pennies and grab again, because I'll probably just grab the same amount that I did before. So we clear those that we've already sampled out of the way. But do you recognize this idea? What happens if I grab a sample of people, put them off the side, grab another sample? Well, this population here is no longer the true population because I've kicked some people out of the population. So I'm no longer sampling the population. I'm sampling a smaller portion of the population. Now, if there are 330 million people in the United States and I sample, 50 at a time, 300 total samples, that's not going to put much of a dent in the 330 million people, right? I'm really not changing the population that much. So what the people in the big gray building decided is that as long as your total number of people is going to be less than 5% of the population, you're fine. You're fine. I've seen this number as high as 10%. I think I've seen it lower than that as well. I guess it depends on what floor of the big gray building you're asking. But as long as you make sure your sample size is not more than 5% of the population size, you're going to be just fine. Okay, so here we go with our example. According to a poll, 42% of people prefer Star Trek over Star Wars. Suppose we obtain a simple random sample of 50 people and determine which voters prefer Star Trek. So when the homework may ask you to describe the sampling distribution, and to describe, that means explain if this is going to be normal and give the mean and standard deviation. Well, it is going to be normal if n times p times 1 minus p is greater than or equal to 10, and if your sample size is less than or equal to 5% of the population. I'm pretty sure that 50 people is less than 5% of the entire United States population, but what about this n times p times 1 minus p greater than or equal to 10? Well, I've got 50 times 0.42 times 1 minus 0.42 needs to be greater than or equal to 10. This is about half, this is about half. Half of 50 is 25, half of 50 again is about 12 and a half. I think we end up with somewhere around 12. Is 12 greater than or equal to 10? Yes, it is. So this is going to be normal. What are the mean and standard deviation going to be? Well, the mean we're going to assume is equal to the population proportion, which is 0.42. And the standard deviation is going to be the square root of 0.42 times 1 minus 0.42 divided by 50, all square root, and we can type that into a calculator and figure out what the answer would be. I think I did that once before, and you get a pretty amazing number, and it's pretty sweet. So that's how you would go through with something like this. And then what can you do with these two numbers? Well, what if I came back and, because you already know that I prefer Star Trek, I come back to you and say, you know what? I did a sample and I found out that in my sample, 60% of people prefer Star Trek. And you could say, you know, Mr. Reeds, I think you're just, you're trying to skew the data because you think Star Trek is better. You could prove that by figuring out the probability of me getting a sample where 60% think a certain way if we already know that the population in general is 0.42. You might find out that it's only a 0.001% chance that I would get a sample like that. And then you can say, see, Mr. Reeds, here's the evidence, you're just full of bunk. And that's what you could do with that information. And in fact, we'll go through that with an example coming up right here. That's just what I said. That's just what I said. You can pause it and read that if you want. Here's our example. This is the last example we have, just a couple of slides left. According to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11, what is the probability that at least 19% are overweight? So you can see what we're doing here. Here is a stated population proportion. and we're going to sample 90 kids, and we're going to see how maybe there's a school that we looked at that had 19% of the 6 to 11-year-old kids overweight. And we're going to say, well, is that unusual? Or is that just about average? And we can probably guess that, well, yeah, 19% is extremely close to 18.8%. So we're probably not going to be surprised that this is going to be just about okay. But let's verify that. And then part B, suppose a random sample of 90 school-aged children results in 24 of them being overweight. What might you conclude? I don't know what we'd conclude. Maybe we'll find out that 24 out of 90 is just fine. Maybe we'll find that 24 of 90 is way too high, or maybe it's too low. Okay, so let's go through these things right here. Our first example, I've summarized both the initial stat and our problem. So 18.8% are overweight, and if n equals 90, what is the probability that our proportion would be greater than or equal to 0.19, 19%? Well, we need to figure out what our mean and standard deviation are. Our mean of our p-hat is going to be assumed to be the population proportion of 0.188. The standard deviation is 0.188 put into the square root of that quotient divided by 90. We find out that it's 0.0412. You can use StatCrunch with these values to find out that it's a 0.48. That makes almost perfect sense. Is it surprising that about 50% of these polls are going to result in a greater than 0.188 and 50% are going to be less than 0.188? That's the symmetry idea of a normal curve. Well, 0.19 is just ever so much greater than 0.188. So we still have about 50% of the samples are going to be more, and about 50% are going to be less than that. So we would look at this and say, oh, that's spot on average. This is just right. If our elementary school had 90 6 to 11-year-old kids, which obviously has more than that, but if our elementary, or maybe you're being silly, Reeds. Maybe we took a sample of our entire 6 through 11. That's first, second, third, fourth, fifth, sixth. First through sixth grade. First, second, third, fourth, fifth, sixth. That's 6 grades. Maybe we took 15 from each grade, right? 6 times 15 is 90. Maybe we took 15 kids from each grade, and we found out that of those 90 kids, 19% of them were overweight. Should Pine River area schools be concerned for our population? And the answer is no, because we're right there in the middle of where we should be. Now, instead, what happens if we found 24 of those 90 kids were overweight? Well, there's no population proportion, there's no sample proportion given. Well, you have to find the point estimate. Remember up here we did the point estimate with 749 over 1745? We just do the point estimate with 24 over 90 to find out that 0.267. 0.267 is a lot more than 0.188. But is it cause for concern? I don't know. Let's see. We're still going to use the same mean and standard deviation as found, because that's based on the sample size and the proportion as stated in the population, right? But then I use the 0.266 with StatCrunch and find out that, wow, that's only a 0.03. I don't know if I still have that window up. The StatCrunch window, yeah, I do. Oh, that's cool how it got small like that. It's weird. You can see how much, how little red there is. It's only a 0.027, 0.03% chance. Very small chance. What does that mean? Well, if you think about this, if Pine River schools were normal, what's the chances of you getting the sample that you got? It's only 3% chance. And if that's less than 5, that means it's not likely. It's a very unlikely event. So what can you conclude? Well, since it's not a normal thing for us to get this, we would conclude perhaps that our school has too high of a population with overweight kids. Maybe that's why, or maybe that's cause for the Centers for Disease Control and Prevention to come in and maybe award some grant money to say you need to educate your families for better eating. That's kind of how things are done. You collect data. That's why you have, I've talked about it before, why you have free well child checkups, right? So we can collect data on populations. But that's how we do the stats on that, and that's what we find, and that is it. However, make sure, and I remember looking at the homework once, they changed the homework now and then. I don't remember there being situations where you couldn't just do the math. In other words, when you do this part right here, do you ever get a situation where the sample size isn't big enough? Just be sure to check that. And they walk you through that, describe the population and make sure that you can. But make sure that you can determine whether you can do a normal analysis. And if it is, then you can use technology. All right, well done. That is the end of the lecture for Chapter 8, which means you now have all of the resources available to you for exam number 2, which is chapters 5, 6, 7, and 8, starting with probability, and then discrete probability distributions, normal, and then samples. I think I made a test, a sample test. I will check to make sure. If I haven't, then I'll make sure that I do. And that test, you've got a lot of time for it. You've got a lot of time to get reacclimated to everything. Chapters 5, 6, 7, 8. Look at those quizzes really well to make sure you're prepared. Look at the test, practice test, and that is scheduled for 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. I think 12, that's right, Easter. Easter Sunday is when everything is due for that. But again, if you do it on the 13th, that's going to be just fine. So schedule your time wisely. Send me an email if you have any questions. Look for that discussion board with lots of different postings for questions that people have. And I look forward to seeing you again. Bye.